beat.
All right, guys, let's get started. We're super excited today to have Filip. He is the CEO and co-founder of Dataware, the main company backing, I guess, TonicDB, which is what I care about, but he'll talk about this Quinine thing today. So this is a good example of a system that doesn't use Postgres and all the wild things you can do if you control everything and not rely on legacy architecture. So as always, if you have questions for Filip, please unmute yourself and feel free to ask at any time. That way he's not talking to himself for an hour. We appreciate him staying up semi-late. It's 9:30 in Serbia. So it's not too bad, but we still appreciate you being here. Filip, the floor is yours. Thank you for being here.
Yeah. Thanks for having me as well. And yeah, as Andy said, like, hi everyone, I'm Filip. I founded Dataware, and today I'm going to be giving you a talk about what's like running databases without the operating system. So in this talk, at the start off, I will first talk about, a short intro about the company. Then I'm going to go over the problem. What's the problem with general purpose operating systems? I'm going to present our solution to that, go into some of the implementation details, and then towards the end, I will, mention TonicDB, like our MVP database that we built on top of this architecture, and then go over some of the benchmarks against the existing systems. So to start off, the research, I started the research about this company in April 2023. And then I wrote first lines of code in May 2024, and we took that as like a founding date of the company. Irina, the second person to join Dataware, joins in December 2024. And then we launched in October this year, or last year, we launched the alpha version of TonicDB. So TonicDB, I'll talk about it more later, but it's a drop-in replacement, so Redis compatible database that's running directly on our hardware manager architecture, so without the operating system. And we got funding in late 2025 and early 2026. And the team since grew to 5 in early 2026. Most of us have some experience at companies like Databricks, Microsoft. One of the guys, the cracked guy, has even a couple of medals from the International Olympics in informatics. So small team, but I think it's a high talent density. And of course, if you think this is something that you're interested in and you think that you can contribute, feel free to email me after this. So to jump straight into the problem that we are trying to solve. So just a quick reminder about what general purpose operating systems are. Those are the systems that you're used to. So think Windows, Mac OS, Linux, FreeBSD, all of them, they're general purpose operating systems. And that means that they're created with this idea that you can run multiple applications on top of them. And they're designed so that the applications between each other, they don't interfere with each other. So they're isolated. And it's very important that they also enforce fairness between the applications and to do that in a secure way. So if you look at the operating system architecture, the brief architecture, very simplified one, we can see that first we have the hardware, then we have some drivers in the kernel itself, then we have the syscall interface, which I'll mention again a bit later, and then we have some of the standard libraries like libc on top of it, and then we have multiple applications running on top. As you can see on the side, we have something that's kernel space and user space, and then we have this border. So first of all, the kernel space, that's where the operating system code is written and executing. So that's the trusted code. And then by the definition of general purpose operating system, everything above this, so everything executing in a user space, is untrusted. So you assume that it's a malicious code, that it tries to interfere with your work. So this boundary, it's very important to be bulletproof as possible. And then I'm going to later mention about the interrupts and the syscalls and how they interfere with the performance of the system. And as I mentioned, like it's written, and they're like one of the best, and most advanced pieces of software ever created, because they can execute so many applications on top of it. But databases are also one of the most advanced pieces of software created, and they want more control. They're not your traditional application. And then what I guess many of us listening to this know is that databases and database engineers try to do as much as possible by themselves, because they know that they have all the context and the operating system has none. Like, I guess the good example of that, and since Andy Powell is here, the famous mmap function. So for example, it's a great abstraction if you're writing a simple application. It's a great utility. However, the problem in a database space is that it's oblivious to what the database is actually doing, and it can it can interfere with security, it can interfere with performance. It's just terrible to use. And since developers of databases know that, they try to implement it themselves. Even though it's more complex, we still do it ourselves because of the performance. And to continue on that, since databases have the context, and we know they have the context, and we don't want for the operating system to execute and do something that we have no control over, we try and take as much control away as possible from the OS. And as a result of that, we have very frequently databases and operating systems fighting, which results in reduced performance. Okay, I guess to everyone here that makes perfect sense. We have something general purpose, then we have a very specific system. It's never going to work that great together. I also want to give some of the more like concrete examples of where you see that. Like the first one, the way that the operating system bottlenecks the performance is the system calls. So recall on this graph, I mentioned that we have this like hard boundary, this red line, between the trusted kernel space code and the untrusted user space code. And now, in order for the applications to do something lower level, for example, that can even be writing to a file, you have to issue something called the system call. Now, system call, you can think of it as an extremely beefy function call. So, for example, the typical function you have, you write your code, you call the function, the instruction pointer jumps to the code that it wants to execute, and it goes on. However, with interrupts, they can occur at any moment. So instead of just moving the instruction pointer, you have to save all of the execution context of the user space, then switch everything to the kernel space. So you have to save your stack, you have to save your registers. Expensively, sometimes you have to also save all the SIMD registers. So you have that overhead of saving all the state and then later restoring it. Or there is also a hidden cost associated with this. And that is, for example, when you're executing your code and then you're in some for loop doing some computation, you have your hot data in cache. And then when interrupt happens unexpectedly, it's going to basically destroy your cache. And then when you go back, you have to rebuild the cache. But this goes even further if you look at this like very popular modern CPUs. Like we have prefetchers, we have branch predictors. Like they're extremely complex systems, and these unpredictable workloads destroy them. The second pretty big OS bottleneck is TLB shutdowns. Now, to understand TLB shutdowns, I'll first introduce what the virtual memory is. So if you think about it, when you have your workstation and then you buy, for example, 8 gigabytes of RAM, very expensive 8 gigabytes of RAM, and you want to put it, you expect your application to have access from 0 till 8 gigabytes. However, if you have multiple apps running at the same time, for example, you can think of it if you have your banking application and then some malicious application. If the bank writes data and all your information on the address, 1 gigabyte, and then the other application can just put pointer to that address and then reads the data, then you have a very, very big security issue. So we came up with something called virtual memory. And that is where every application can have its own virtual memory address space. For example, you can think of it like you have physical memory address from 4 gigabyte to 5 gigabyte. And in applications virtual address space, you can map it from 0 to 1 gigabyte. So those two addresses are not connected. You can map them however you want. Now, you might ask, like, how do you do it? There is a system called page table. You have some page table entries, which tell CPU this virtual address is actually this physical address. And then to speed everything up, because modern CPUs are ridiculously fast, you have something called TLB, or table look-aside buffer. You can think of it as a sort of like a cache for the system where you can enter the virtual address and it gives you back the physical address. So it works very fast and it's very simple. Now, one very important thing to know about TLBs is that every CPU, so every core on CPU has its own TLB. So if you look at this example, for example, this is a very simplified example where we have 3 cores. Each core has its own TLB. TLB contains the information that virtual page X maps to physical page Y. And then we also at the bottom of the screen have the main memory. So that's, let's say, some sorts of truth. And now, for example, you're executing your thread on core 0, and you free the memory. Your OS wants to take some of the memory back. It can unmap the page X from your virtual address space. In this case, now the page X is no longer in your address space, and to enforce isolation, you cannot access it anymore, etc. The problem is because the cache is per CPU, all the remaining cores have the wrong entries. And now what can happen, for example, is someone can access the stale data and they can read actually the private data for your application. So what operating systems does is it uses something called interprocessor interrupts. So recall I also mentioned that interrupts are slow. And now how we solve this problem is the core 0, or the core that has the invalid entry. It sends the interrupts to all other cores in the system with the stale data. And then those cores have to acknowledge that and say that they flushed their cache. And only then can we go back to executing the actual application code. which adds huge overhead. Again, this is a very simple example. You might think like, okay, that's 2 interrupts. It's not too bad. But imagine if you're running a database on a system that has, 256 cores, this can become quite expensive. The next, common OS bottleneck that I can mention is the fair scheduling. So in the OS, since it's built with this idea that it has to be fair towards any application that's running on top of it, we have something called preemptive scheduling. You can think of it like this: you have your task, your process, and then the CPU picks it. It allows it to execute. And then after a certain unit of time, it gets kicked off the CPU. This is done so that one malicious application, if it didn't get kicked off, one malicious application could lock your whole system. Now, important thing to note about fair scheduling and preemptive scheduling is that they're fair in a sense that if you have one CPU and two apps running, both apps are going to get 50% of the CPU time. However, they're not fair in terms of performance. So what can happen in a very bad case is that you get yielded at a very critical point when you're just about to release a lock, and then other threads waste time. And that's what I wanted to show in this example. So we have 4 threads. First, we're executing thread 1. The code is super simple. We do something, we acquire the lock, we do something else, then we release the lock. Now what happens is, for example, thread 1 is executing, it acquires the lock, it does some computation, and then here the preempts happen. So it ran out of time on the CPU, and in enforced fairness, it gets kicked off, even though it only had to do one instruction and then release the lock. And then the thread 2 gets put on the CPU. Now it does something, it tries to acquire the lock, but thread 1 holds it. So it, again, gets yielded off the CPU, but we wasted some time there. Then thread 3 tries to do the same thing, do something, acquire the lock, you fail because the thread 1 has it. Then the thread 4 again does the same thing. So you do something, acquire the lock, but you cannot acquire it because of thread 1, and then you get kicked off the CPU. And then finally, with just like fair scheduling, thread 1 gets picked up again. And as you can see, we just increment one number and then release the lock. And that's it. Now we get again kicked off the CPU. But the point here is that we only had to do like these 2 simple instructions. But what happened is, okay, like now, for example, we execute thread 3, it goes into critical section and then continues the execution. But what happened because of preemptive scheduling is that we got kicked out at very inconvenient times if you look at the context of the application. Like we knew that we only had one more instruction, critical section, and we were out, but we get kicked off anyway. Then with these like red boxes, we can effectively say that they were suboptimal scheduling. They were kind of like wasted CPU cycles. So yeah, like there are countless more examples of how operating systems might interfere with your application and the performance of the application. But I think that we can put them in 2 big groups. The group 1 is just the general overhead of having the operating system beneath your application. So think about all the syscalls and the fact that when you want to write to disk, you have to issue an interrupt, then the operating system does. So that's just the overhead of the operating system. And then the second, which I think is maybe even more important, is the lack of semantics. So if you think about it, because the OS has to, put all these abstractions and artificial boundaries against what you can do, then even though you have the context and you can do something more optimally, you're not allowed to because the OS prevents you from doing that. I think those are the 2 big groups, and these are just some of the examples that I showed. So I guess like now we can just, jump to our solution, and that's QuinineHM. So QuinineHM is our implementation of hardware manager architecture. Now, the hardware manager architecture, we define it as a thin layer of code that creates a single tenant runtime exclusively for databases. Maybe better to say for one application. So if we go back to this image, we can see on the left side, we can see this architecture of the operating system where we have kernel space, user space, bunch of layers. And then on the right-hand side, we can see actually the hardware manager, where the database, instead of being on top of and having these like limits, artificial limits between the kernel and the database, we actually tightly couple them together. And your database is now actually running at the bare metal speeds. In terms of how we architected the hardware manager, we came up with this idea of bare metal primitives. Now, bare metal primitives are hardware manager subsystems that cannot be optimized further. So when we started, architecting the system, we realized very quickly that we have some things that we just have to do. For example, booting the computer, setting up the memory, setting up the interrupts. Those are things that are dictated by the hardware, and you cannot optimize them based on the application. So what we did is we came up with this idea that Hardware Manager can only contain these bare metal primitives or things that it absolutely has to do, and it cannot be optimized further. Now, one maybe not so logical example of that is the networking protocols. You might think, like, sure, the networking stacks and the BSD sockets and all of that, that can be improved and that can be optimized depending on the application. But TCP protocol itself, it cannot be because then you're not, you don't adhere to the TCP standard. And now on top of these bare metal primitives, in order to allow for this like semantic execution of the database, we provide transparent APIs where we want to allow database to control absolutely every aspect of its execution. So it can touch absolutely everything in these bare metal primitives. The example, maybe not a good one, but you can read your NIC device queues. I'm not sure why you would do such a thing, but we allow you to do that. And then you can, optimize some things around that. Now, in order to build
I
this
mean,
system,
are you going to go more detail on what it takes to support these different drivers? Because like I'm thinking like NVMe drives are just way more complicated than SATA drives of 10 years ago.
yeah.
Uh, in order to get the full amount of parallelism out of them, like that's not a I don't know. I guess maybe I just don't understand how much is in the driver in software versus down in the hardware. But like,
Mhm.
would for would you have to for every single hardware device, are you spending a lot of time writing these different drivers, or you just say I'm going to only support like these small set of hardware devices?
Yeah, so I have one slide later on when I talk about the networking, but
Okay,
the idea is we only have a limited hardware support, so only the hardware that we want to target. So sure, we're going to target the NVMe, but we're not going to target some, the older device drivers and all of that. So we're very limited in what the hardware we actually want to support.
but I mean, it's more than just say like I support NVMe because I think that's even that's an abstraction layer above versus like I'm going to support this vendor's like a Samsung drive versus a Western Digital or Seagate.
Yeah, of course. Like you have to optimize then the driver for the specific one. For example, like our target devices, it's public cloud. So we want to optimize our drivers depending on, for example, what AWS is doing with their EC2 instances. So you
Got
optimize
it.
for those like specific configurations.
Okay. All right. Thanks.
Yeah. So yeah, as I was saying, like while we were developing the system, we came up with a couple of core design principles that we wanted to follow while we were designing this and writing this code. The first one is that we want to question absolutely everything. One of the important things to realize is that if you look at some like done system like the OS, you might think that all the problems are solved, but lots of them, those are abstractions that they came to be because of some of the limitations of the hardware of the past, or some assumptions that OS has to take in order to do, multiple isolated applications. So you have to question, is that truly the best way to do things? And now sometimes we find out that yes, that is the best way, but very frequently we also find like, no, that's or hardware abstraction or that's some, legacy thing, or perhaps it's because of the constraints of the environment. The second thing is, and it might be our more controversial one, it is that we do not want to support POSIX. So we don't want Hardware Manager to be POSIX compliant. Why? Because when you think about it, POSIX is truly just adding some artificial limits around what you can do with the hardware. And if we want to expose the bare metal primitives like we want them to in its fullest form, we cannot add these artificial limits. So we decided not to support POSIX, and that turned out to be one of the best decisions that we made, because that's actually what allows you to do semantic execution of the database. And the third and final thing, which I mentioned a couple of times, is because we want to allow, the systems running on top of Hardware Manager to have the raw performance, we want to give them the control over absolutely everything that we can. So we want to expose absolutely everything. I also wanted to quickly mention behind here, like I mentioned that Hardware Manager is built out of these bare metal primitives and things that cannot be optimized further. But we noticed there are some of the things, for example, we ported a couple of memory allocators like memalloc, dlmalloc, and some others because we want to be able to, compare and benchmark. And for example, we ported boring SSL from Google for the encryption. We ported, some of the Prometheus implementations. So we found out that there are also these add-ons that we want to make available to QuinineHM so that you don't have to write absolutely everything from scratch if you don't want to. And now I want to jump into some of the memory management, some of the implementations behind the hardware manager. So we wanted to, one of the most important system parts of the system is of course the memory. So we wanted to really nail this one down correctly. Now, to understand how we designed memory, we first have to look over some of the constraints that we know we have. The first one is that we're only running one application. And because we're only running one application, we don't benefit from having multiple address spaces. So we can actually use just a single address space. Also, one very interesting thing is because there is only one app running, you don't have to give memory back ever, which can be fairly useful when designing some of the systems, because on traditional operating system, your app is executing, it allocates a lot of memory, and then it has to free it so that the rest of the applications can use it. But if you're the only one application, who are you giving your memory back to? Like, no one. So we know that as well. And when we were also like defining some goals, we wanted to fix issues associated with TLB, which is of course TLB shutdown, but it's also in more general like TLB pressure. We also wanted to make it super simple to port and write malloc functions. And we of course wanted to use good security practices. Now to understand some of the security implications of memory, I want to show you how it looks like to get your memory layout, the physical memory layout from your bootloader, for example, grab2. So the boxes in blue, those are the available, that's the available memory, the one that you can actually use. Then red is marked as reserved, so you should not touch those ever. And then you also have somewhere in your memory, you have the binary. Now the thing is, if you use just like this physical memory layout as your virtual memory layout, you have some of the possible security issues. The first one, of course, is the arbitrary code execution. If you can write to any address in space, you can just put the pointer where you want it. You put some malicious code inside of it, and you call it as a function, which is of course very bad. The second thing is catching null errors. Actually, the thing is with null errors, it's mostly like a human abstraction. Like the address 0 in hardware is perfectly valid one. So you actually have to put some system in place to catch this like null dereferencing errors. And to do that, we came up with something that we call double memory mapping system. Now, there is a lot of information on the slide, so I'll take some time here to explain as much as possible. So on the top of the slide, we can see that that's the physical memory layout. So again, we have the blue boxes that represent the available memory, red is reserved, and we also have binary somewhere inside of that address space. Now, the first memory mapping that we do is identity map. The identity mapping means that you take your physical memory layout and you map it directly as is into virtual address, so identity one-to-one. Now, the problem with this one is that you have your binary. So if you map it just like any other, memory address, anyone can, as I mentioned before, can, write some machine code and then do arbitrary code execution. So what we want to do is to map those pages as read-only and executable. Everything else in the system is non-executable. So we know that, we push some of the arbitrary code execution issues down to the hardware level. So if you try to write something to the binary, it's gonna send you a page fault. If you try to execute the code that's outside of this memory mapping, you're again gonna get a hardware fault. Now, to fix some of the issues associated with TLB, recall I mentioned that we want to fix the TLB shutdown and we want to fix the TLB pressure. TLB shutdown, it's really only an issue if you have multiple address spaces across multiple cores. It's not really an issue if you only have one single address space. You don't have to care about TLB shutdown. So you kind of, by having one address space, you get rid of that issue. The second issue that I wanted to fix with this memory layout is we want to decrease the pressure. Now, the pressure means like any other cache. Like any other cache, you have limited space. So if you have a lot of small pages, you're gonna frequently have to do some page walks to get the new page address. So what we do is we use a lot of 1 GB pages. Those are huge pages. They're available on all the modern CPUs. However, in order to ensure that we catch the null errors, the first page, the first 4 kilobyte page, we don't map it so that if you try to dereference the null address, we actually get the page fault. And then also around the binary, we use 2 megabyte pages because we don't want to waste a lot of memory with 1 GB pages. And now this way, now you might wonder, like, why did we do identity mapping in the first place? Well, that's because when you're writing lots of low-level code, you have to deal with a lot of memory mapped I/O. You have a lot of special addresses that are dictated by some hardware specifications. So it's beneficial as a developer experience that you actually have your physical virtual addresses be identical to the physical ones. Now, the problem with this is once we start implementing the malloc functions. So the first problem that's sort of the most visible one, is what happens with fragmentation. So imagine that these two blue boxes are filled, and then we have just these first two blue boxes left as available memory. If we wanted to allocate memory that's larger than the first chunk, we would get an error, like there is not enough space, even though there actually is enough space to allocate it. So in order to solve this fragmentation issue, what we do is we take all the available memory, and then we map it for the second time at the high addresses. So now what we end up with is we have the one-to-one mapping at the actual physical addresses, and then at the really high addresses, we have mapped only the available memory. Now, this allows us, for example, when we're porting the malloc function, when we are initializing the malloc function, we can tell you that this is where your memory starts, and this is how long it is. If you run out of memory, we actually run out of memory. You don't have to give it back. It's all up to your control. And this makes it super easy to port malloc. So we have multiple mallocs ported, including DL malloc, me malloc, and we're probably going to port a couple of others. But it also makes writing your own fairly trivial. One other thing that we wanted to kind of improve on over the existing systems is just, general caching. And to do that, when we are mapping these high addresses and high pages, if we have two pages that are physically next to each other in memory, we're going to put them also virtually next to each other in this high address mapping space. And this way, we managed to create the memory management system that keeps the flexibility that you need for low-level programming, while also having it super simple and super efficient to do, your more advanced allocations for the database and malloc ports. The second thing that I want.
Sorry, go back to this. Yeah. So why put? Because I think in the hardware lets you intermix. I mean, one thing is be a line, but you could intermix like you have clear regions, like you have the small pages, 2 megabytes, and the 1 gigabytes. That's your sort of memory region. But like you could put the binary basically at the beginning of the memory address. And, like I understand you're putting for address 0, that special case, you want to catch that. But then why put the binary in the middle in between the small pages and huge pages?
That's mostly like just for the illustration purposes. Like the point is with 1 gigabyte page, the problem with 1 gigabyte page is that the first 1 gigabyte page, if you don't map the initial from 0 till 1 gigabyte, if you don't map it with 1 gigabyte, then the first 1 gigabyte page that you can map is starting with the address 1 gigabyte. So then all of the first gigabyte, you actually have to map it with those smaller pages. Then what it pays off to us is to map binary at 2 megabyte boundary. So then we can use the 2 megabyte pages. So that's why we do it this way.
Got it. That makes sense. And then we have the small compacted pages. Can you remind me again? What is that?
Which ones?
So on the
These ones
bottom,
at the start?
on the
Or
other side, right there.
the compacted?
Yeah, look, you said small compacted. Remind me again what that was.
It doesn't. The small, yeah. So that's, for example, because we want to sometimes focus on having those like huge 1 gigabyte pages physically next to each other when possible. Then we might take, at the start where we have a lot of those smaller pages, or sometimes if we have the smaller pages around these reserved sections, we want to map them at the end so that we don't affect the cache locality.
It's like padding, but like instead of useless data, it's small pages.
Effectively, yeah.
Got it. Okay.
Yeah.
Thanks.
Okay, yeah. The next thing that I want to talk about is threading. So as I mentioned at the start, the preemptive scheduling is not necessarily the best way that you can, create this multi-threaded system, and it can actually frequently be the bottleneck for databases. So like one other system that you can use is called cooperative multitasking. That is when instead of leaving it up to the operating system to send you an interrupt once your time on the CPU is done and then kicks you off, you are actually the one who says when you're done with the work. And that way we can avoid those situations that I mentioned where you get kicked off the CPU just as about to go out of the critical section. Now, in order to allow for that, the QuinineHM exposes the bare metal primitive, the threading bare metal primitive. This is just a small snippet of the API, but we have a huge API. And one of the functions that we have, for example, is scheduler yield. So that you can call it and then you go out of the CPU. But also to prove some of the optimizations that you can do is when you're doing the classical yield, in order for your application to continue executing after you're back to the CPU, you have to say all the state. That includes the registers, that includes the stack, but also sometimes expensively it includes your SIMD registers. And to save SIMD registers, you have to call the xsave instruction. Now, in order, sometimes we notice that that's absolutely unnecessary to do when you're at the end of the execution loops or you just call some other function. So we also provide scheduler yield ABI. So in, not to get too technical, but there is something called system v ABI, which is what, all the systems are following basically. And you have some quality saved registers. That's only a couple of general purpose registers that you have to save. You don't actually have to save, your SIMD registers and a bunch of others. So that's, for example, more efficient. So with this API, we allow the hardware manager allows the database to actually implement the exact model it needs. So you can do cooperative multitasking that I mentioned. You can still do preemptive one if you want to do that, but you can also do the hybrid threading, which is my personal favorite, where you use the combination of cooperative multitasking with the preemptive multitasking.
So don't compilers try to look at least like, I guess the internet compilers don't know when they don't know the region in which you did a bunch of work, and therefore whether what registers you need to save. Uh, but in theory, you could start putting logic, or you could expose like a coroutine API to developers using your hardware manager, so such that the compiler could figure out that you don't need to save the SIMD registers or other things, right? Instead of having explicit calls like this.
Yeah, but I'm not sure if I understood the question. But for example, if you want to yield the CPU, is that what you're asking about? Like if you want to start executing something else?
So like with preemptive scheduling, the idea is like you don't have to write code and say, I know
Yeah,
I'm yielding. I mean, you can call it explicit yield, but like since in the program application code, you don't know like the entry point of when the thread started executing.
yeah,
So therefore you don't know what registers you touched, and therefore
yeah,
they just dump everything out. But potentially you could expose an API of like, here's some block of code that it'll run, and it won't get preempted, and then the compiler could say, okay, for this block of code as like a coroutine, I know what registers I've touched because I had
yeah,
to write the instructions to do that, and therefore I know which of these schedule yield calls you want to
yeah,
invoke. Right
yeah.
now the data system programmer has to know explicitly which one of these they want to call, but the
Yeah.
compiler could figure it out.
Yeah, sure. That would be the more advanced implementation. Like what we were thinking is with this system call, with the system via ABI. Thing is, when you call the memory, like the compiler already knows that it has to save all the registers except a couple of them. So already do the work for you, and then you call the function, and then you know that compiler already saved everything that you touched and that you touched before and that you need afterwards. And then that way we can only save a few without having any extra overhead. But yeah, I agree with you. If you do that, that would be the more advanced implementation of this.
Yep, thanks.
Yeah. Yeah. Now networking, I also wanted to mention the networking, and you asked this question a bit before about hardware and supporting multiple, different devices, different vendors, etc. Like at first, when I started this, I thought that this will be a major problem. Especially, for example, I was mostly worried about the networking cards, especially because networking is a key of any application, and you want to optimize it as much as possible. So I thought it will be a big challenge, but then I realized since we're targeting public cloud, all of the major cloud providers like AWS, GCP, and Azure, they have one driver, one networking card and then if you have that one driver, you can execute across of all their compute. For example, on AWS, you have to implement something called Elastic Network Adapter. And if you implement that, you can use internet on all of the EC2 instances. So it ended up to be not such a big issue as I originally thought. Now, I mentioned at the start of this presentation about how interrupts are slow. Now, I didn't have any data to back it up there, but I wanted to show you an example on the networking side. So when you're doing networking, you have two options how you're going to write your driver. You can write it to be interrupt-based or pulling-based. Now, interrupt-based means if you get the package, so you get your TCP package, then the device, so the NIC, sends the interrupt to the CPU, then CPU stops what it's doing, it handles the interrupt, and then goes back to what it's doing. So that's traditional interrupt-based. But then there is also more advanced ones called the pulling-based systems. And instead of the CPU waiting to get notified via the interrupt by the networking device, it's actually actively checking, hey, do you have a new package for me? And when we run the benchmarks, in the blue color, it's pulling based, and in red, it's interrupt driven drivers. As you can see in throughput section, the pulling based can achieve more than 300,000 requests a second, whereas the interrupt driven can only achieve 37,000 a second. And also, if you look at the latency of pulling based systems is very flat, very predictable because you're constantly checking it. Whereas if you're having interrupts, you can have interrupt storms and a bunch of other factors, and then you have like these like huge P90 and P99 latencies. However, using pooling is not a silver bullet that's going to solve all your issues. When I was doing some of the benchmarking code, I left accidentally the pool-based instance running all night. Then I got banned from one of the cloud providers because I was using 100% of the CPU the whole night, and they thought that I was mining the Bitcoin, so they limit my access. So the actual solution to these problems is to use a hybrid approach. Again, hybrid approach is something that's usually the best. And here you want to use pooling and interrupts to maximize the throughput. What you do is when you're not having any packets, you turn on the interrupts, then you receive the first packet, and then you wake up the CPU. The CPU starts the pooling threads, then you're pooling until the new packets are coming. Once they stop coming, you go back to the interrupt-driven mode. So when you have no packets, you're using 0% CPU. When you have a lot of packets, you're using a lot of CPU, but that's seen as a legit CPU usage pattern. And that way you can maximize the throughput safely, even in the public cloud. And to finish this section off about hardware manager, I wanted to compare hardware manager architecture against some of the existing architectures. So I want to compare it across a couple of features that I picked here. One of them is direct hardware access. So can you actually work with your NICs and NVMe drives directly? Second one is do you do hardware multiplexing because that does the overhead. Now, the third and very important one is do you implement POSIX? Because you implement it, you don't allow for the semantic database execution. And do you use single address space? Because that's the best way to mitigate all the TLB issues. So the first one that I want to compare is Linux. Now, Linux does somewhat allow you to do the direct hardware access, especially via the DPDK and SPDK. It allows you, it has some limits, but yeah, it allows you to do that and nothing else. The second one is something that some people here might be familiar with, and that's the unikernels. Now, unikernels, for those of you who don't know, it's a very tiny kernel that's made to execute only one application. The problem is, if you look at all the implementations, the reference implementations of the unikernels, they want to take your Linux binary and then execute it as a single application. The problem with that is in order to achieve that, they have to implement POSIX because they want to take your binary that's implemented for the POSIX system and then execute it on their system. So they do have direct hardware access. You would have one address space, you would have zero hardware multiplexing, but you're not able to implement semantic execution because you're constrained by POSIX standard. Now, the more aggressive implementation...
Let me interrupt you. You've said semantic database execution, and again, maybe you define it. I missed this. What do you mean by that?
Yeah, by that I mean, for example, that your database can control how your system behaves. So it can pick which thread is executing, when the thread can be on the CPU, to have more fine-grained control over the devices or the implementation of the networking stack. So it has more control over how it executes. For example, we do the example of scheduling because that one is the easiest to explain. You want your database to be able to say, I want this thread to execute, then I want this one, and then that one, instead of it sort of being like a black box that just picks which thread is executing. So that's what I mean by semantic execution.
Okay, thanks.
Yeah. And then we also have exokernels, which are more aggressive implementations of unikernels. Now, it's been difficult to fill this column for exokernels because there's not a lot of reference implementations. It's been developed by MIT in the 90s, so a while ago. But for what I could find is yes, they allow you to have direct hardware access, and from what I've seen, is they do not implement POSIX. Now, again, this has only been done in academic purposes, so who knows, the implementation of that, how it will look like. What I know from that implementation is that they do hardware multiplexing, so you don't have also the single address space. So, it's not clear, could you do the semantic database execution or not, because I just didn't have enough reference implementations to test it out. And then, of course, we have hardware manager in the end, which is, of course, the system that implements all of those. So I just want to make distinction between hardware manager and the rest of the databases.
All right, we have a question in the chat. Nevin asks, how does the hardware manager approach compare to microkernel operating systems?
Yeah, well, microkernels, again, they implement, now that's a completely different architecture from the general purpose ones, but they still, if you look at this, they still want to do, they don't allow you to do direct hardware access. They do hardware multiplexing. They usually implement the POSIX standard. They also have, multiple address spaces. That's just a different way to create, the general purpose operating system that can execute multiple applications, where you want to have better stability while executing. So I think it's more similar to Linux than to anything else on this list.
I mean, actually, be more similar to like a unikernel because in theory, you could write database stuff in user
You
space and
could,
lands
yeah, you
there,
could write it as a part of the operating system, as a module.
but
Yeah,
that's sort of exokernel too. Yeah, the lines are blurry.
yeah, yeah. Okay.
So a quick
And
question right here on that slide.
yeah,
Sorry, I don't know what happened to my camera. Uh, but the how do you deploy this in the cloud on AWS? Is this like an AMI image or what's the
yes.
deployment?
So on AWS, you just generate an MAI image and then you boot it up as any other operating system.
Got it. And then do you run into trouble with trying to manage that service because many of the tools aren't quite really well uh, developed for AMI and stuff like that? Or what's your practical experience with that? And maybe if you're going to touch on it later on, you could just delay that part.
Of developing with on the cloud. So creating the AMI images and all that. Is that your question?
Yeah, so when you're trying to manage it, right, AWS has all these bunch of tools that will let you figure out when your service is not running well.
Yeah.
Look at the network traffic, all of those things. How well do they work with when you're deploying it as AMI?
Yeah. So from our experience, if you go to the monitoring and all of that, that still reports very accurate numbers. So you have still that support. So we haven't run into any trouble of that. We also do some of our observability on our side as well. So I cannot accurately answer that question on other services provided by AWS. From our experience so far, we ran into no issues when using some metrics from AWS. And
Okay,
also in terms of developing the AMI images themselves, the AMI import function from AWS is extremely slow, so we wrote our own that does it a lot quicker.
got it. Okay, thank you.
I'll jump in because I have kind of a similar question, related question. So, like in general, let's say you run Postgres on an RDS instance, you're able to SSH into it and talk to a Postgres daemon, right? But now that
Yeah.
you don't have multiple processes, I'm wondering like, how does that part work?
So it depends like what you want to do. Like in this system, like the question is, why would you want to SSH into it? So the way that we do it and solve this issue is that we dump as much data as possible from the system to your host machine. So you can use all the tools that you're used to from your host machine. So we dump it in the correct formats, and then you can do what you want with the data.
But like, I've never owned a database running in production, but I would think that, I don't know. I feel like it's a thing that people SSH into the currently running database to try to do, I don't know what. Like, isn't that a problem?
Yeah, well, again, if you're, hosting it yourself, and especially if you're doing something like self-hosted, that is an issue. But then you also have a lot of, database services out there that you cannot SSH into, and it's sort of everything is hidden away from you. So it's not something that's necessary to run in production, I would say.
Okay, thank you.
Yeah. Okay. I guess, we're also running a bit out of the time, but at the end of the talk, I wanted to mention TonicDB. So as I mentioned at the start, the TonicDB is an in-memory database. It's Redis compatible database. It's designed to be a drop-in replacement for Redis. That means that we implement Redis serialization protocol. All the commands that we implement are following the Redis documentation. So you could theoretically just change the link in your, environment files, and then everything still works the same way. We implement over 170 commands, all the basic data structures that you have, but also then Bloom and Geo modules. So a decent implementation of Redis. As I mentioned before, we launched it as a whitelisted alpha in October 2025. Now, what you could do with that is you had your typical cloud, interface, cloud dashboard where you can do one-click deployments. You had your console where you can connect and talk to it via the Redis protocol. You also had a bunch of graphs where you can follow, the networking traffic, the RAM usage, CPU usage, etc. One thing, however, that I want to note is we launched the whitelisted alpha in October 2025, but about a month after that, we closed the whitelisted alpha down. That was because the TonicDB was always just an MVP to prove that our tech that we are building on the hardware manager side is working. It was never meant to be like our key product. So the implementation of it is quite scrappy, I would say. Like there is nothing ridiculously impressive about it, and it hasn't been developed since the whitelisted alpha. So this is our internal version, the last internal version that we published, and it was in September of last year. So I just want to have that in mind when we go over some of the benchmarks in the future slides. So yeah, the architecture, the simplest way that I can show it is that per CPU we have one thread running. So it's one thread per CPU. And then for those who don't know what Redis is, it's a key value store. That means that for every value you have a key associated with it. It acts as some kind of like a very big hash map. You can think of it that way. And then some of the typical functions, commands that you can do is, for example, get set, where you would set the value for a key or get the value for a specific key. And then what we did is we created like this huge hash table that's backed by extendable hashing. We also use my favorite hashing function, the XX hash 3. And then we have like this huge global state that's actually keeping all the data. And then we have thread per CPU. And this, of course, as most of people here can see, it's a very bad implementation. You're going to have a lot of threads fighting over the same resources because you have like this huge global state. One thing that we are using, for example, that's not being done by other databases is it's implemented as fully cooperative system. So we never use preemption in the system. And that way we try and mitigate some of the effects that you would have with the contention. Now for the benchmarks that we ran, the configuration that we used is 100 concurrent clients with 1,000,000 requests. And to keep the benchmark fair, we randomly generate keys and values before we start the benchmark. And then in order to simulate some of the locking contention that you're going to get in production, we made each client use the same set of keys, so they're all fighting over the same resource. And now for the part of the benchmarks, which I guess everyone is curious about. So as a baseline speed, we took Redis, of course, is the main implementation. So it does on our benchmark, it does about 300,000 requests a second. And then we also compared TonicDB against DragonflyDB and Garnet. Now, DragonflyDB, as I'm sure most of you here know, is like a modern implementation of Redis, so multi-threaded implementation of Redis. And if you look at its architecture, it's a lot more advanced than the one of TonicDB. For example, they're using the shared nothing architecture, if I'm not wrong. That means that they are trying to reduce the locking contention as much as possible, where every thread is basically its own instance, so you don't have to use the locking mechanisms that you have in our system. So it's an incredibly advanced, and it's a startup that only does this type of database. And they're able to achieve about 1.2 million requests per second, or 4.2x faster than Redis in our benchmark. And then the third database that I want to compare TonicDB against is Garnet. So that's Microsoft's implementation of key value store. If hardware primitives can be further optimized, hardware subsystem variations, new networking protocols, ISA extension, etc. Where do you see as the biggest hardware optimization opportunity?
Let's hold off on this at the end because
Okay.
there's a general question. Let's get through the benchmark first.
Okay. So yeah, as I was mentioning, like we have the Microsoft Garnet, so their implementation of key value database against lots of engineers, lots of work, and by our benchmarks, it was about 4.6 times faster than Redis, doing about 1.4 million requests a second. So just a bit faster. And then on this benchmark that measures overall performance, so across all the commands that are implemented, TonicDB is able to do 1.8 million requests a second, or 4.9, almost 6 times faster than Redis, and about 4,000 requests a second faster than Microsoft's Garnet. So even in this like very bare bones implementation, very unoptimal implementation of key value store, we are able to beat these systems by having less overhead of the interrupts and TLB showdown and all the things that I was talking about before. Now,
How many cores was this?
how many cores? It was done across, I believe it was 8 cores.
So Redis is running 1 core, Dragonfly, Garnet, and Tonic are all 8 cores. Got it.
Yeah. And then the next benchmark that I wanted to mention that I think is interesting and more relevant in the database space is actually the L range command. So as I mentioned before, the Redis has it's a very bare bones database, and you have those simple commands like get and set. And what get does is you send it your key, it parses the key, then it hashes it, gets you value, and then returns the response. So it's very light on the computation side on the database. But if you look at the other databases, they're doing a lot more computation on the side. So they have to parse more complex language, they have to do some query planning, they have to manage their buffers, so much longer lived tasks. And this larrange command, what it does, it returns X elements from the list. So it goes through the list, classic list from your programming languages, and then it returns a certain number of elements from it. So it's the closest thing in Redis that we have to a longer running task. So I want to include it here as well. And then the Redis does 54K a second. The Dragonfly DB does about 6.9 times faster, so almost 4,000 requests a second. The Garnet, Microsoft Garnet, does about 500,000 requests a second, so about 9 times faster than Redis. And then TonicDB does 1.1 million requests a second, or 21 or 22 times faster than Redis, almost 3 times faster than Dragonfly, and more than 2 times faster than Garnet. Now, in this case, what contributes to this huge performance gap? First, if you look at the slide before, Dragonfly DB wasn't this much faster on average. And that is because Redis has a very bad implementation of list. So they're using your classical linked list, which is going to be terrible for your caching. Dragonfly DB, Garnet, and TonicDB, they're using more advanced implementation of the list, where you're using arrays and then you link arrays together. So you're able to use somewhat of caching and some other features of the CPU. However, when you're executing Dragonfly and Garnet, you still have this overhead of your threads constantly switching. You have the interrupts, you have your networking stack of the operating system, so you have a lot less control of the execution. For example, when the interrupt happens and your cache gets destroyed, you have to repopulate the cache, and then you're closer to what Redis is doing. Whereas in TonicDB, because we're implementing the cooperative multitasking and it's mostly hybrid-based networking, so you very infrequently get the interrupts. We're able to keep that cache locality much faster, and that's where most of this improvement comes from. And yeah, that's about it what I had for this presentation. So again, thanks for listening, and we can now go over all the questions, or later, if someone's watching on YouTube, you can send also the email.
All right, I will applaud on behalf of everyone. Filip, that was fascinating. Let's open to the audience first. Jignesh, you're interim opportunity. You get to go first, and then we'll cover the questions in the chat. Or Nevin and Victor, if you want to unmute yourself and ask them, you can go for it.
Great. I thought that was a really nice talk. If you look at the performance gains that you had, do you have a sense of where the gains were coming from? Because these are all different systems with different implementations. So
Yeah.
could you attribute it to it being more efficient at the OS hardware level, or were you seeing in these other existing systems that you compared with that they had a lot of, let's say, TLB shoot down? Are you able to do any root cause analysis in terms of where the gains are coming from?
Yeah, so the most analysis that I came from, I mentioned that at the end. For example, for the first benchmark we were doing across the all the commands, where we are about 6 times faster than Redis and much closer to what Dragonfly and Microsoft are doing. I found that most amount of improvement that we're coming from is from faster networking stack, from a more optimized networking stack. So that's where the most performance is coming from there, especially because we have a very trivial implementation of key value store. It's where I found out that the most performance is coming from. And in the second benchmark, where we're having this longer running task against Redis, I mentioned Redis has a very bad implementation of a linked list. So the cache is, it's absolutely not utilized there. And then you have a lot of, tracking pointers, which is terrible for performance. Then if you look at Dragonfly, DB, and Microsoft's Garnet, they have a much smarter implementation, which uses, a linked list that's backed by arrays. So you're still able to utilize some of the cache locality. But then what we do at TonicDB is we also implement this more advanced data type where you have linked list backed by the array. So we utilize the cache. But what I found out is sort of like the cause of this most performing gains is networking stack, plus the fact that our data, when it gets into the cache, it gets used. What I think that's happening, especially on the Dragonfly system, is that it gets switched a lot, and then threads get yielded off the CPU, another one is executing, and the cache gets polluted quite a bit, and then they're not able to utilize all the benefits that we are. So I think that those are the two main causes.
Great. Thank you.
Nevin or Victor, I can read yours if you want me to.
Hi, this is Nevin. Nice to meet you. So my first question is, how do you think about error handling or fault tolerance? For example, if you have a request that misbehaves or causes an issue, would that cause the entire system to crash? So for example, a key application of operating systems is like process isolation. How do you think about that for your system?
Yeah. So I want to learn more about the question. Like, what do you mean by a request misbehaving?
Well, for example, you have an emphasis on cooperative execution between threads. But so I'm just thinking about what happens a if there's I'm just assuming like, if anything that could go wrong will go wrong, like just taking the
Yeah.
Murphy's Law example. So, what happens if you have a misconfiguration? Do you have any runtime protections against that, or is it all based off of your like testing and validation strategy?
Yeah, so for this database, it was mostly about our testing and validation strategy. And I agree. Like for example, like hypothetically, in a situation like could it happen that cooperative multi-scheduling fails and that some thread takes the CPU forever? Like maybe it can happen. And what how we tested it is with a lot of the fuzzing and a lot of simulations, and then we saw that it doesn't happen. But yeah, in the newer implementations of Kinian, as I said, that this implementation is quite old from September last year. What we do is we always implement, for example, the hybrid threading, where we know even if something misbehaves, we have this protection that it's actually going to get yielded at that point from the CPU, and the rest of the system can continue working. On the other hand, for example, what you might ask is if TCP we get some bit flips, or if we get some other faults that are not necessarily the application level. Uh, like the way that we solve that is we look what does the Linux do? What does the Linux do in this situation? Does it, crash your application? Does it, crash this whole system? And then we try and implement the similar behavior on our system as well.
Thank you. That makes sense. If I can ask a follow-up question. So I'm
Sure.
very impressed technically in that you have such a high throughput and performance on the single node for say Tonic. But I'm wondering more from like an end-to-end perspective, like as a system or an application developer, where do you see your hardware manager or something like Tonic, like delivering the most like end-to-end value for a user or like a company.
Yeah. So like we have, I guess, at the core, what Hardware Manager provides, you have like two key value propositions. One is the performance, and the other one is cost. So in terms of performance, as I mentioned, you have your benchmarks. Then if you're executing a bunch of, microservices in a region on AWS, you're going to have a lot of, traffic. And then if you have reduced the latency, the whole system is going to be running faster, which in performance critical applications is quite important. Then the other thing, which I guess, is going to come more into play as we develop more advanced software, that is if on a single node you can process more requests, that means that you need overall less hardware to process the same throughput, and therefore you need less in server costs. Your AWS bill gets smaller.
Thanks. That makes a lot of sense. And I can see like if we have some very latency sensitive application, Tonic would be great if we for like minimizing some cache layer. So I think that's a great argument. But I really think it would depend on the specific context as to how if whether it would be worth it. But I'm very technically impressed. Thank you.
Okay,
Thanks.
so I will read Victor's question. He asks, if hardware primitives can be further optimized, hardware system subsystems variations, new network protocol, ISA extension, etc., where do you see the biggest hardware optimization opportunity could be to support QuinineHM better? Like, I guess basically, what should you focus on next to optimize?
Is that the question, or like if we could optimize the hardware? I'm not sure
Uh,
that I understand the question. Like,
Yeah, there's a lot of hardware software co-design ecosystem. There's a lot of like new protocols being developed for network, new
Mhm.
SL, RISC-V, etc. So everything can be changed. So my question is, you said your one of your slides says hardware primitives cannot be changed anymore. My question is, if hardware can be changed, where are the optimization opportunities?
Yeah. So what I said is like that the hardware primitives they cannot be optimized further, so they can be changed depending on the hardware. For example, what Andy mentioned about different NVMe vendors having some of the different features. Like you could have hardware primitives or the drivers for each one of them, and then you extract the most amount of performance. But the idea is once you implement the driver, for example, Samsung NVMe drive, there is nothing that the application itself can do with its context that's going to speed that driver up. That's the goal. So in terms of the hardware, if the hardware changes, the thing remains the same. Like you optimize it as best as you can for that specific hardware to execute so that the database or the application running on top of it with all its context cannot optimize it further.
Okay, so okay, is there anything that similar to Linux operating system that you just have to get rid of it so it'll be a lot better for hardware? Is there anything for hardware optimization that can be done?
I'm not sure, like you mean for a
For
specific
example,
type of hardware?
memory hierarchy, for example, that's very important for AI workload. Is that something that's also very important for your database, your hardware manager?
Honestly, I'm not sure how to answer this specific question. So maybe you can send me an email and then I will think more about it
Yeah,
to give you an
send
accurate answer.
Yeah, thanks.
Yeah.
All right, Hugo, let me read his first question, and then his second question I'll roll into my question. You mentioned you're limited by the number of hardware drivers you have them implemented. Is this the same for hypervisors? For example, did you have to write logic specific to AWS Nitro and then for the Azure equivalent, or do you just use virtual I/O and everything, and it works for everything?
Yeah. So in terms of, for example, at AWS, we hadn't had to develop anything specific to it. So everything that works on our local machines in our virtualization environment work on the AWS, except of course the drivers. For example, the elastic networking adapters we have to write specifically for AWS. And then in terms of Azure, we still don't have the Azure support. But from what I've read, for example, they're using the hypervisor, and you need to do some specific things to tweak it to execute there. But we still haven't done the Azure support, so I cannot give the accurate answer to that. What I know for sure is that Azure also has their own custom networking card that you have to implement in order to execute on their system.
Got it. And then his next question is, and this is related to my question, and then we'll finish up. How do you do your debugging profiling outside of the POSIX Linux environment? Are you able to use GDB, perf, etc.?
Yeah.
Do you build your own version of these tools? And I guess the larger question is like, although you're not POSIX compliant, to expose malloc and free, you have to be sort of C compliant, right? So like,
Yeah.
is that the abstraction? And then does somebody get then to use all these tools?
Yeah, like for example, in terms of like let's do the question like the debugging and profiling. For example, we do most of that work on our like the local system, so we do it on our Linux machines, and there you are able to use GDB for debugging, so you can set your breakpoints, see the call stacks against all the SMP cores, so that's you can lean on the existing environment. And we also had luck with the fact that you can run perf on this system and you're gonna get the accurate data from it. So we can use some of the existing debugging and profiling tools when we are developing it. But then also, for example, when we wanted to do some sampling at the runtime, for example, to build the flame graphs and things like that, we had to implement that ourselves. Then we dump it to disk, and then we dump it in such a format that the existing Linux tools can pick it up and then visualize it and extract some insights from that. So yeah, like we use a lot of the existing tools. What we care about is saving and dumping all the data that we need in order to use those tools, basically. That's the second part of that question.
Got it. Okay. All right. My last question is, well, at first I was going to ask, like, how would someone implement like a classical buffer pool manager in this? But there is sort of a larger question of like, should your hardware manager just do that, right? Like, yes, someone could plug in whatever replacement policy they want, but in terms of like mapping logical page IDs to frames in memory, because you're already kind of doing that for your virtual to physical addresses. So why
Yeah.
not just expose that, and then as a buffer manager that someone can then build upon? And then likewise, like, is the long-term plan for this to be only used for database systems, like things that are data-intensive applications, or do you see this being as a more general purpose thing? And if it's the former, if you want to keep it like targeted for database systems, could you expose functionality like here's a schedule implementation, and then someone can just plug in the different policies that they want or whatever, right? Because and I know
Yeah.
you said you're not a unikernel. Then it basically is what you have is actually a unikernel. It's just not POSIX compliant, so it doesn't smell like the unikernels of the old days.
Yeah. Yeah, so I mean to answer the first question about the buffer pool management, since we were implementing the Redis compatible database, we didn't have to worry about that too much.
Yes.
So we didn't spend enough time for me to answer that question at some high level. I've seen some papers about how you can use you can improve caching with the unit kernels. So I guess there is a lot of space there, what you mentioned. And then the second question that was about, do we keep it as a database only thing, or do we allow some of the other things as well? We will try and keep it. The current plan is to keep it as close as possible to data infrastructure. So not only databases, but maybe some of the pipelines for perhaps the load balancers for Postgres, MySQL. So something that's connected to the data infrastructure. That's the current plan that we have. Yeah, was there another question?
I guess my point is like, should you then start providing, again, classical services like a buffer pool manager that
Yeah.
maps the translation layer? Like, should your hardware manager start exposing that? And obviously, you have different hooks so people can place policies, but the core functionality is there.
Yeah, again, we haven't spent much time thinking about it just yet. So there's definitely something interesting. I can see what you're saying, that it could be quite useful.
Okay.
Like to just swap it out the same way that you're trying to do with the mallocs at the moment. I can see that being quite useful. But I guess, maybe if we come in a year for another talk, then I can give you a more accurate answer.
Yes.
Yeah.
All right. I guess my last question is like, I mean, the theme of this whole seminar series is like Postgres versus non-Postgres. It's clear you can't do any of the shit you're doing in Postgres, so that's not a question. I guess if you're not actively working on the Redis port, can you share what's next?
Yeah. We cannot. It's still private.
Okay. Fair. Okay.
But it has something to do with the data state and, of course, the AI and a couple of other things.
Because everything is, of course, yeah.
Yeah.
Again, I think you have a unikernel, but it's a very, very narrow API that doesn't need to support like a bunch of other stuff, right?
Sure.
So very cool stuff. Again, Filip, thank you so much. This is fantastic.